So now the calculation for the anion in the gas phase has been converged. Now let us calculate the electron affinity. Let us start and take an Excel sheet. This is, let me write it here, this is neutral, this is anion, and this is A. So this is my anion energy. Remember, I am taking the free energy because I want to take both the contribution from the electronic energy as well as the 0-point energy correction. Let me check the neutral also. This is my final Gibbs energy. Let me copy it for the neutral, and of course this is gas phase. And now if I calculate the AEA, this is neutral minus anion and I want to see it in EV because my experimental value is in EV. So this is what I get. Gas phase is 35 eV. Now let us check the solvent phase. So the easiest way to do the solvent phase calculation is to take the anion input file. Now I can and convert into a PCM, CPCM water, and I can start from the anion geometry. I call it U anion echoa dot INP. And I can run it. Actually, I have already run it because it was taking a long time. So this is where the output file is. If I open it with Chemcraft, this is how it looks like. Don't get perturbed by this low energy frequency. It's happening because of a not so tight optimization. You do this optimization tightly, this low energy frequencies will go away. But if I want to see the with the difference how it is different from the gas phase geometry, so we can go one step back. and then we can use this utility structure comparer, get RMSD of the two structure from the chemcraft window. So it's 0.08 is the average thing, and it's mostly the position of the hydrogen atom which actually undergoes a significant change in this case due to the formation of the anion. So what happens is that whenever is this extra electron get attached, this actually gets to one of the antibonding orbital, and sometimes it leads to a proton loss. So that's why this shows into a maximum change in the case of hydrogen. So you can always compare the geometries and of the neutral and the anion, or the anion in the gas phase and the aqueous phase, to do this kind of calculations. Now I can take the free energy values from here. I can open it with Notepad. And similarly, I can do the optimization for the neutral also in the aqueous phase. And if I do that, so the adiabatic electron in the adiabatic electron affinity in the aqueous phase is 2.33. Now go to the actual experimental value is 2.94 to 3.40. So generally these PCM based methods can give you pretty bad values. However, if you do an explicit solvation, of course doing explicit solvation actually requires a lot of this extended sampling procedure, you can actually give very good answers with respect to the experiment. Now, if you want to avoid all of this sampling procedure, you do not want to do this sampling by doing MD, ORCA these days provides an easier option in the form of ORCA solvator. It uses random trial and error to assign the placing of the solvent, and this algorithm actually uses information from the self consistent EQ charges as a part of extremely simplistic potential to guide the placing polar molecule in a more reasonable ways, and solvent molecules are placed as close as possible and maximizing the electrostatic energies, electrostatic interactions. This helps to create the solvent cell in such a way that it does looks like the actual result one would expect from a more elaborate calculation by doing proper sampling. Now, the keyword for this, of course, it is easier to use this kind of protocols in a much cheaper way and then re-optimize it. So, you can use this XTB alpha B solvation model to do that, and so depending upon what solvents you are giving here, it's will going to provide the corresponding solvent molecules around, and the keyword is solvator, and this number n solve determines how many water molecules you are going to put. So, let us do one thing, let us take the geometry of the uracil we are using and then put 3 water molecule by doing this kind of calculation. So, this was my original uracil geometry. We can open it with the is not able to read because it does not contain the number of atoms. So I can copy this keyword, uracil solvator .inp. So I can submit the job. So this is what it's trying. It is trying to putting the water and trying to minimize the electrostatic potential. Okay, so the job has been complete. It actually total took 21 minutes, and the final geometry has been saved in this uracil solvator dot solvator. So this is an XYZ file. If you open it with, let's say, Chemcraft, this is how the configuration will look like. You can see there are 3 hydrogen bondings. You can see there are 3 water molecules hydrogen bonded to the uracil. Now you can optimize it in a separate method. and do the calculations. In this case, of course, you can also include the PCM solvation outside this one. So, you can take the microsolvated structure and then use PCM on the top of it. In the case of electron affinity, they do not lead to very good answers, does not really give any improvement over the thing you get over normal PCM, but there are cases where the water molecule explicitly interact with the solute, and in that case if you take a hybrid model where you surround first the solute with some explicit water and then treat the continuum with the PCM, they generally give you much better answer. So, this is what we wanted to discuss for the week 11. So, in this week you have came to know about how to take care of the solvation both implicitly and explicitly. We are more focused on the implicit solvation because they are more easier to use and black box. We have seen how solvation actually affects geometry and properties. We have found out how to find solvation free energies with Cosmo RS model. We have seen how solvations can be modeled for the excited state and how it lead to shift in the peak. And we have seen if you want to do the explicit solvation, how you should place the water molecule easily by using the Orca solvator model. So, in the next week, we are going to take care of the things which are left. See you next week.